Hello, in this video we are going to discuss about microstrip transmission line. So this is one of the most popular type of transmission line which is mainly used in PCBs. The main importance of this microstrip transmission line is because of this planar structure. It can be easily fabricated using photolithographic process, and it can be easily integrated in with the PCBs, and it can be connected with passive and active microwave devices. Because using these planar transmission line, it is very easy to connect to the antennas when the antennas are designed on a PCB. So here we are going to the details of microstrip transmission line. So let's see that. So when you consider a microstrip transmission line, you can see that this is the basic structure it will be having. So these yellows are representing the metal. So it will be having a trace which is made up of the metal, and it is backed by the grounded dielectric. And this dielectric will be having a thickness, and W is the width of this trace, and epsilon R is the dielectric permittivity. L is the length of this microstrip line. So the main mode of electromagnetic wave propagation in microstrip transmission line is Quasi TEM. That is because when you consider the field in these lines, so this is the cross section of this thing. So here we have a cross section, and when the wave is propagating through this trace, the wave will be not only propagating from the uh, trace to the dielectric, some of the waves will extend from the trace to the air and then to the dielectric. That is, there will be some fringing occurs. Due to this fringing, it will not be supporting the pure TEM mode. That is, in TEM mode, electric field, magnetic field will be perpendicular to each other, and they will be perpendicular to direction of propagation. Here you can see that the electric field is not that much perpendicular. It can have the components in the air and inside the dielectric. So we know that when you consider the wave propagation inside the dielectric, the phase velocity will be Vp is equal to C by square root of epsilon r, because it has an dependence on this dielectric. And when you consider this wave propagation in the air, the phase velocity will be equal to uh, speed of light, because this is air, it does not have any dielectric impact. As the wave is both propagating in air and this dielectric, it will not be supporting pure TEM mode, and this propagation we are calling it as Quasi TEM mode. So these solid lines represents the electric field, and the magnetic field will be forming the loops around these traces. So this dotted line actually represents the magnetic field. As these fields are extending into the air and into the dielectric, the effective dielectric constant will be having the influence of the dielectric and that of the air. So it will be epsilon E equal to epsilon R plus 1. 1 is the dielectric constant, relative dielectric constant of these uh, air, and it will be equal to epsilon R plus 1 by 2 plus epsilon R minus 1 by 2 into 1 by square root of 1 plus 12 d by w, where d is the thickness and w is the width of the trace. So when you consider the structure as a whole, having the effective dielectric constant epsilon E, the phase velocity can be, so sorry, this is not in dielectric, the phase velocity of this Quasi TEM. So this is not dielectric, this is the TEM. The phase velocity of the Quasi TEM wave can be given by the expression C by square root of epsilon E, where epsilon is the effective dielectric constant. And the characteristic impedance of this trace can be given by the expressions. These two expressions here, you can see that there are two equations. That is, it is a piecewise function, and it is divided into two parts. One part where W by D, where this width to depth ratio is less than 1, then we will be using this equation to calculate the characteristic impedance. If it is more than 1, we will be using this equation. And here you can see some constants. These are some experimentally calculated values. As this propagation is Quasi TEM, these are not theoretically calculated values. And I forgot to mention that one of the main conditions that we have to consider while designing the microstrip transmission line is D should be very, very less than the wavelength. So this is one of the main condition that we have to consider. And next is the threshold frequency. Because in previous slide I showed that D should be very, very less than or less than the wavelength of propagation. So when the frequency increases, what will happen is this D will be comparable to the wavelength. So at that time, uh, these waves will be causing some type of surface waves. So because of these surface waves, the wave propagation will not be purely Quasi TEM, because it will be having the combination of surface waves and these Quasi TEM waves. Because of that, these type of transmission line can be operated up to these threshold frequencies. That is, after this threshold frequencies, these waves will be contributing to the surface waves, and because of these combinations, it will not be purely Quasi TEM. That is why when we are designing a microstrip transmission line, that will be working up to this frequency. After this frequency, there will be both surface waves and these Quasi TEM propagation. And this frequency is known as the threshold frequency. So the transmission line that we design will be working up to the threshold frequency. So this threshold frequency is similar to the cutoff frequency that we have seen in case of the coaxial cable, because in coaxial cable we are having TEM, pure TEM modes, and when the frequency increases, higher order mode of propagation will be happening. So similarly, as it is the case of Quasi TEM, this will be causing the surface wave. So this threshold frequency is similar to cutoff frequency in case of the TEM propagation in coaxial cable. And next one shows the equation to calculate the parameter W if we know the thickness of the substrate and the dielectric constant. Usually we will be knowing the thickness of the dielectric and permittivity of the material, and we have to calculate this trace width when we are going to use these type of transmission line to feed the different types of antennas. So in that cases, these are the two equations that can be used. So this is also the piecewise function. Here you can see that it is divided into two regions for W by D less than 2 and W by D greater than 2. So if it is W by D is less than 2, we have to use this equation, and if it is greater than 2, we have to use this equation. Here in these two equations, two constants are used, and these constants are A and B, and which can be calculated using these two equations. So when we are going to use this equation, we will not be having any idea about this ratio, because this is the unknown that we have to calculate. W is our unknown, so we won't be knowing where W by D is less than 2 or W by D is greater than 2. So when we have to use this equation, one thing that we can do is, after calculating A and B, start with the first equation, assuming that W by D is less than 2, and start with that equation, solve for W by D. So then we will be getting W by D, and if that is less than 2, we can go with this equation. If it is not less than 2, then again calculate with the second equation. That is how we are calculating, using these two equations to calculate the parameter W when we know the epsilon R and D. So let me show an example. So here we have to design a microstrip transmission line having characteristic impedance. Sorry, 50 ohm is the characteristic impedance. I forgot to mention it here. So 50 ohm is the characteristic impedance on FR4 substrate having thickness on 0.6 mm. So the first step is now what we are knowing is we know the thickness D, we know the characteristic impedance is a 0. So first step is we have to calculate A. So this is the equations to calculate A. Here we know the parameters like epsilon r as it is FR4. We know the epsilon r as 4.4. So substitute all these parameters and calculate A. Here it's a 0 is 50 ohm. That is our aim. Then calculate B, substitute for these parameters and calculate the value of A and B. So now we have the values A and B. Now our aim is to calculate W by D. So first we will be starting with the first equation assuming that W by D is less than 2. Now we don't know where W by D is less than 2 or not. So use this equation, substitute the values of A and the calculate W by D. Here you can see that when after calculation this value is less than 2. So our assumption is correct. So we can calculate W by multiplying this value into D. So in our case D is 1.6 mm. So we get the trace width W as 3.06. So this is how we are calculating the trace width when we know the characteristic impedance and the dielectric constant, thickness and permittivity. I hope you get some idea about what is transmission line and what is the mode of propagation in the transmission line and what is the main thing that we have to consider while designing the transmission line and what are the characteristic impedance and threshold frequency, etc. Thank you.